Hi, everybody. Welcome to today's online meetup, How to Develop and Operate Cloud-Native Data Platforms and Applications featuring electronic arts use cases. My name is Amelia, and I'll be your moderator. Before I introduce you to our speaker, we have to cover a couple of housekeeping items. All participants are automatically on mute throughout the session, and we will be using Slack to communicate. So please take a moment to join us on the community Slack channel, which is copied into the chat box and is at alluxio.io/Slack. However, if you are having trouble joining Slack, feel free to message me your questions anytime instead, and I will share it with the group. In today's session, our speaker will be diving into two different projects that he has led at EA. We will have a Q&A session at the end so we can answer all of your questions. To ask the questions, a reminder to join the community Slack channel, but you're also welcome to use the GoToWebinar control panel questions tab to submit your question. Now, please don't hesitate to send your questions anytime. There's no need to wait till the end. Lastly, today's session is being recorded and will be available for on-demand playback. We will email you the link to the presentations as well. That's it for housekeeping, so let's meet our speaker. I'm very pleased to welcome Du Li, who is currently an architect of data infrastructure at Electronic Arts. He worked in academia and industrial labs for many years after earning his PhD from UCLA. Prior to joining EA in mid-2018, he was a software engineer at Yahoo and Apple. Without further ado, please welcome Du.
Thank you, Amelia, for the introduction. So my name is Du. I work for Electronic Arts, or EA. Many of you may be familiar with EA from the early days when you started playing EA games. So these are some of the beautiful EA games we recently launched, like around last year. EA is one of the top producers of video games. So as many other gaming companies and other internet companies across the industries, we capture some of the interaction events when a player is playing games, and then aggregate those events or data in the cloud data center, and apply AI and other data technologies to process data and learn about the user behavior, player behaviors, and then loop back to improve engagement and the player experience in general. So at EA, every year we have several game launch seasons in which we launch a few new games, and so every time we launch a new game, we observe a lot more data traffic than usual. And every day, we also observe a surge of data traffic in some of the peak hours. So that said, we are experiencing seasonal and daily fluctuations in data traffic. And we have many Black Fridays. It's not just one day, one season, or a few hours in a day, you get a lot more data. But this kind of fluctuations are interspersed across time. So to address this big data challenge, we have to be able to scale up and down our computer resources frequently and quickly when processing the data. Obviously, those are for reasons of performance and cost, right? We want to keep the best performance optimal. At the same time, we want to keep the costs low. So in order to do that, we build our data stack, tech stack in the cloud. It is roughly divided into 3 layers: applications, platforms, and infrastructure. In the cloud, or in any software engineering practices these days, we have dev aspects in which you have to build, test, and write code, etc. And we also have ops aspects in which you have to release software, deploy, operate, and monitor. So in general, we want to automate the ops part because it's sort of similar across different projects. We want to keep the operational cost minimum, trying to automate things so that the team can focus more on dev, which is more creative and presumably more fun. However, in reality, this is not always the case. So especially this is a new thing in cloud computing. So we often observe similar DevOps problems in cloud-based tech stacks. The reason is that we see varying degrees of automation across different layers. At the infrastructure layer, I think more or less the major providers like AWS, Google, and Microsoft, they already adopted the practice, standard practice like infrastructure as code. So pretty much everything is automated. So often a few clicks away, you can launch hundreds or thousands of machines and services. They are just all the machines are provided for you. However, this is often not the case in the platforms and the applications. They are way much behind. I think one good reason is the infrastructure providers like AWS, they're making money out of that, so they have to automate everything. But platforms and applications tend to be developed by smaller teams. The incentive economically is much lower. So as a consequence, we often see very high operational costs in platforms and applications. One part of the reason is some of the platforms and applications lack built-in automation, so it's very difficult to scale up and down. And often there's a mismatch of automation across different layers. So it's very difficult to keep different layers in sync. Like the case, infrastructure is automated, but platforms and applications are not. The consequence is that the engineers are very busy with operations. They're busy resolving tickets and alerts all the time. There's very limited time for dev and technical innovation. To solve this problem, fundamentally, we have to redesign the system in a cloud-native architectures and adopt the best practices for automation. So in this talk, I'm going to present two stories. One is about how we develop, rebuild a monitoring system at EA, and another one is how we trying to rebuild our data platforms at EA. So in particular, I want to show you in these two stories how data orchestration helped solve the problems at a lower cost and elegant some way. So to see the problems with DevOps, just imagine you have a busy mom taking care of thousands of crying babies every day. So when we started looking, revisiting the monitoring system, we were receiving more than 1,000 alerts every day. And the infrastructure team was completely turned into an operation team. They didn't have any time for tech innovation, but just resolving alerts all the time, and the team felt so depressed and overwhelmed, and the retention rate was very low. So to solve the problem, first we have to understand how a monitoring system is like. A monitoring system is typically consisting of three types of components. At the bottom, you see we have metric sensors. They are running on every host in the system, and then aggregate the collect and aggregate metrics. And those metrics are aggregated at the metrics aggregator. And then there's at the top, there's an alert generator that periodically check conditions in the matrix aggregator and generate alerts. So each component here has some configuration. The matrix sensors need to know which what matrix to collect and where to send the matrix to. The matrix aggregator needs to know from which machines to collect matrix, and the alerts generator needs to know which machine runs what and how to do health check, things like this. So here we see a big mismatch of automation across different layers that is causing the operation nightmare here. In the monitoring components, those components are manually configured. There was little or no automation at all. At the infrastructure layer, everything is fully automated because we build things on top of AWS. Computers can be added and removed with only a few clicks away in seconds. And this mismatch makes it very difficult to keep configuration up to date. Then there's a consequence. We are seeing many false alerts because some machines no longer exist. They're already terminated, but the monitoring components are not updated yet. They're still trying to check this terminated instances. At the same time, there are many new resources added into the system quickly, but the monitoring components are not updated to monitor those new resources. So at the same time, many resources are not monitored. The consequence, even worse, is that because of this overwhelming amount of alerts every day, nobody or no team can handle it. So we often observe major outages in the systems. So we solved this problem by introducing a configuration orchestration layer that trying to keep the monitoring configurations in sync with the hardware status. And this is sort of a middleware, right? Middleware layer. We are not modifying or any underlying monitoring components. We just change the configuration and automatically generate the configurations. So to explain a little more about this project, let's look into this architectural diagram. So in the middle of this is a bunch of auto configuration generators. We generate configurations for the three types of components in the monitoring system: alerts generator, matrix sensor, and the matrix aggregator. So those generators, they take inputs from different sources. First is we get a host map from AWS periodically, which tells us which machine runs what kind of services. And we also needed to know how the monitoring components are wired, how they're connected together. And on the right-hand side, you can see we need like a library of methods of how to check services and machines. And we also need a kind of a specification what to check for each cluster. And at the end, those generators, configuration generators, would generate configurations for all the three types of monitoring components. And we automate this using CI/CD pipelines, so that anytime we change anything, change any of the configurations, or on the AWS side, any hardware machines are updated or changed, then the changes can be pushed automatically by the CI/CD pipelines to the different deployed to the different components, so that everything is in sync. And by doing this, we fundamentally eliminated the kind of alerts that was overwhelming. So to recap the principles in this project, this project is called monitoring as code, in the sense that we're treating configurations as the same level of citizen as code. they're also first-class citizens. All monitoring configurations are managed as one GitLab project. And then on top of that, we impose standard structures on all the configurations such that they can be automatically generated. The configurations are treated the same way as software code, first-class citizen. The updates are treated the same way. They are reviewed, and everything is traceable. And they are automatically deployed by CI/CD pipelines. Essentially, this is just an orchestration layer on top of monitoring components without modifying any of the components. Certainly, we're also not modifying the infrastructure. So to see the impact of this project, so in the beginning of last year, on the left-hand side of this curve, the chart you can see, at the beginning of last year, before we deployed our solution, we were handling more than 1,000 alerts every day. Of course, most of those are false alerts. And then after we deployed the first the solution to the first big cluster, you can see a sharp decline in the number of alerts. So by end of April, after we deploy the solution to all the compute clusters, the alerts were reduced from 1,000 to about 100. At the same time, of course, the number of hosts and the services were increasing, right? And then after a few more iterations since the summer of last year, we have settled down to a couple of dozen alerts every day on average. And then in the past 1,000 alerts cannot handled by a team, and now it's only like one on-call person from the team can handle it. So after we solved this monitoring headache, the team can spare some resources to explore some new problems. So this is the second story I'm going to tell you, how we are trying to rebuild the data platforms at the EA. Again, it's also using data orchestration technologies. So as I just said, we were generating 1,000 alerts every day. One major problem is the tech stack was very old. You can see this are two of the compute clusters that we run different workloads. The left-hand side is running ETL workloads, and the right-hand side is primarily running analytic workloads, ad hoc queries. So these two clusters are sitting on top of S3. So all the data eventually is stored in S3. But on the left-hand side, you can see we are using HDFS, Yarn, Hive, Woozy, this kind of pretty traditional stack. And on the right-hand side, we have part of the cluster running in Yarn, Hive, and part of the cluster is already upgraded to more modern technologies like Presto. So to summarize the issues, we need to understand a little more about the two clusters, what they are doing. On the left-hand side is a cluster called Ocean that is running internal ETL jobs. It only cache is recent data in HDFS. We only need to have a few days, 3 or 7 days of data in HDFS. And the ETL jobs read and write on HDFS directly. Because if you directly go to read and write on S3, the performance will be very bad. So there's a lot of variance in terms of speed. But those jobs need to back up data to S3, and at the same time, we need to update the analytics metastore of availability of new data so that the ad hoc queries can proceed in the query. There's a newly available data. The left-hand side version is more like a legacy tech stack. Has Hadoop, Yarn, Hive, Woozy, and Metastore, etc. The right-hand side, we have two generations of technologies mixed together in the tech stack. So on the right-hand side, the cluster is called Pond. It supports external customer workloads. Basically, these customers run analytical queries directly on S3 because those queries can involve the entire history of data. So we have to directly do this on S3. Some of the queries are turned into lightweight ETL jobs because some of the customers may feel they run a query and feel it's necessary to do this periodically, so they turn that into a lightweight ETL job. And some of the analytical ETL jobs have dependencies with the regular ETL jobs. One example is Spark. We have many Spark AI jobs running on this Yarn cluster. They need to analyze potentially the entire history of data. And then they generate something that will be consumed by other ETL jobs on the left-hand side. So because of the data namespaces are different. One is on HDFS and another one is on S3. So the synchronization between the jobs is actually convoluted. So we can already see a few pain points here in this legacy architecture. First is we have to maintain two clusters with duplicate functionality. Actually, in the real system, we have more than two clusters. We have 5 or 6 clusters with a lot of duplicate components. It's a nightmare to upgrade and operate these different clusters. And also it's a waste, right? Because you have to pay for all the duplicate components. Another pain point is Hadoop is very difficult to scale. It was not designed to scale at the speed we need. We have to do this multiple times a day, a week. I have to do this frequently and very quickly. But Hadoop wasn't designed to do that. One reason is HDFS is used as cache here. We are using HDFS to hide the speed variance in S3. And then when the data is residing in HDFS, we have to persist the data to S3 and also have to clean up the disk space frequently. So it's a lot of hassle. HDFS is used as cache, but it was not designed for caching purposes. So that means we have to implement a very complex custom code for data backup, purge, retention, and loading. We need to load data manually to the cache whenever it's not there. All these functions are just basic functions if you have a specialized caching service there. The fourth problem here is the address spaces are fragmented across different clusters. We are using HDFS for caching recent data. They are serving primarily the ETL jobs. And we're using S3 for the analytical workloads to access all the data, the entire history of data. So to do this, we must maintain 2 half metastores. One is for ETL and one is for analytical workloads. I think the technical guys should be able to understand this. If a table is residing in HDFS, then you have to, in a half metastore, you have to set the table location pointing to HDFS prefix, right? When the data is in S3, your half metastore have to pointing all the table location to S3 something. So the address space is fragmented. And one consequence is you have very complex synchronization between jobs, and also between the half meta stores in different address spaces. So many headaches we need to resolve in order to move forward. Fortunately, we have something called Alluxio, which is providing data orchestration for the cloud. So on top of Alluxio, you can see many computer engines like Presto, Spark, Flink, Hadoop, and a lot of many other things. And underlying Alluxio, we have different data sources like HDFS and S3. So the nice part of Alluxio is it can provide you a unified address space. So your computer engines no longer need to care where the data is located. You just need to know. You can just trust Alluxio and amount of data in Alluxio address space. Then your Presto or Spark or Hadoop engines just need to know my data is in Alluxio, and then we can access it. Beyond that, of course, Alluxio started when Alluxio started, it was meant to be a caching service, right? So you cache the data, and you get the performance of caching. So inspired by this, we decided to introduce Alluxio as a data orchestration layer and rebuild our data infrastructure. So as you see in this architecture diagram, we are consolidating all different workloads for ETL and ad hoc queries and analytic workloads. We have, but doing this, we consolidate 5, 6 different clusters into one. One cluster can host all the different types of workloads. And we use CI/CD for automatic deployment of all the components here. After introducing Alluxio, we can completely get rid of HDFS. So YARN can be adapted to be auto-scalable. Presto, we can do the same thing as a modern stack, so it's much easier. But the magic here is we can turn YARN and Hadoop into auto-scaling cluster technology. And the fundamental enabler here is we're using Alluxio for data orchestration. So this layer sits between the different engines like YARN and Presto, and the AWS tiered storage S3. So the data is cached into Alluxio on demand, and it provides a unified address space. So we can immediately see a few benefits of data orchestration here. On the analytics workloads, we are using Alluxio together with Presto. The primary benefit is we're using caching for better performance. And of course, recently, Alluxio introduced a new catalog service that provides some data transformation and automatic aggregation of small files that can even improve the performance better than just caching. On the ETL workload side, we have replaced HDFS with Alluxio, so that we have a new combination, YARN plus Alluxio, that is more scalable. So there are quite a few benefits. For example, we are introducing specialized cache service to automatically backup, purge, and load data. All those features came with Alluxio. It's different from HDFS. If we use HDFS for caching, but it was not designed for that purpose, then we have to implement complex custom code for those basic functionalities of caching. Alluxio also provides one unified address space, so that synchronization across different workloads is much simplified. And we only need one half meta store because all the data now can point to S3 or Alluxio. And another important benefit here is we can much more easily scale and auto-manage computer resources so that we can get better performance at the same time. We can minimize the costs, not just the CapEx, but also OpEx. Then there's a bigger problem where we lose performance after getting all these benefits. So in order to answer that question, we did some preliminary benchmarking experiments last year, comparing the performance of Alluxio versus HDFS. So we adopted the same configuration with 10 H1.8 instances in WS, and we collocate Yarn and HDFS for Alluxio. We configured Alluxio to use 3 replicas of each data object, and we are not using memory for caching. That is, we are using hard disks for caching, which is supposed to be the worst case for Alluxio. And in the test data set, we have several different type of workload. Once we have a single file, but varying the sizes from 1K to 500 megabytes or something like that. And we have one single table with 1,000 files of varying sizes. The sizes also varying from 1 KB to 500 megabytes. So we run several different workloads, reads, writes, and also have queries. The reads workload just load data from S3 to Alluxio. And this turns out to be 3.3 to 4.7 times faster than loading data from S3 to HDFS. In the writes part, when writing data from Alluxio to S3 is around 3 to 4 times faster than writing data from HDFS to S3. And we also run have queries end to end. So if the query is running reading data from Alluxio and writing data to Alluxio, it's a couple of times faster than reading data from HDFS and writing data to HDFS. So as you can see, in general, after we replace HDFS with Alluxio in the Hadoop stack, the performance can be several times faster. So to conclude this talk, we have a few takeaways. First is in a new cloud age, the old ways of DevOps are breaking. So if we are using the wrong technologies or using the right technologies in the wrong way, you can pretty much end up in spending 20% of the time doing dev and 80% of your time doing ops, if not worse than this. So this distribution of DevOps efforts have strong implications on CapEx, OpEx, and also HRX. CapEx means how much money you spend on your hardware, right? OpEx is how much you spend on operation. And HRX is often ignored by technologists. When your engineering team is spending 80% or more time resolving alerts and solving all the operational overheads, your engineers will be bored. They'll be frustrated and feel unproductive. They will leave. Then you have to hire replacements. Actually, that could be a lot more expensive than your CapEx and the OpEx combined. So the new emphasis in the cloud is automation. We adopt all kinds of cloud-native technologies like Kubernetes, CI/CD pipelines, GitLab, etc. So the purpose is to automatically deploy software in much shorter cycle, you be able to auto scale your system and even automatically recover from the bad situations. In the end, you may improve the situation to like spending 80% of your time in dev and 20% or even less time in ops. So the situation will be significantly improved. However, we can do even better than this. I think one bigger point is automation is good, but if we have to automate on the right things. There's some examples. I think nowadays, pretty much we are all the service providers are treating their infrastructure as code. So at the infrastructure level, everything is automated. But I think we can do similar things to platforms applications, also treat them, the configurations as code. Then you can, many of the problems can disappear, can be mitigated at least. So in this talk, we overviewed 2 projects we have done, we have done or are doing at EA. One example is configuration orchestration, in which we automatically generate all the configurations to keep the hardware and the configurations in sync. And that in that project, we improved the daily number of average number of loads from 1,000 to around 20. And then in the second project, we introduced Alluxio for data orchestration, which comes with caching, specialized caching functions and improve the performance, and also it provides a unified address space. So those features give us better performance, at the same time simplify the architecture, and more fundamentally reduce the operational cost. Because once you have the right architecture, then many of those alerts will not generate at all. Okay, so that's the end of my talk. Thank you. I'm ready for questions.
Great, thank you, Du. We have quite a few excellent questions here, and just a reminder, you're welcome to submit your questions through the GoToWebinar control panel under Questions tab, or you can simply post it into the Slack channel under the General channel. All right, so our first question here is, I'm also working on my company's data platform, and we have the similar challenges of needing to maintain many clusters, very inefficient and duplicated efforts. So this person is looking to re-architect the system, and the question for Du is, do you have some general advice on how to go about a project at this scale, or any unexpected or especially challenging things that you came across?
Okay, very good question. I think rebuilding a lot of legacy system is not a trivial task. It should be a major organizational investment, and also, so I think engineers tend to be very technical. They're trying to focus on the technical problems and propose new architectures. It was cool. But I think my advice and experience is with a project at this scale, it's also very political. You will have a lot of you have to handle a lot of organizational issues. For example, you have to spend probably most of your time bringing the entire organization to the same page, convince them of your vision, and you have to do a lot of communication. So I think the biggest thing I learned here is in order to carry out move forward the project, you have to pay a lot of extra cost on the handling the organizational issues, in addition to the technical excellence.
Great. Our next question here is specific to one of your earlier diagrams, Stu. You had a diagram where you show pond and ocean. And in the diagram, the question here is, you have a Presto gateway. Is that the Lift Presto gateway? If not, which one is it?
The Presto gateway is one of the is an open source project as well. So when we have multiple, Presto is something different. You have to when you introduce Presto in your tech stack, you have to operate and maintain multiple Presto clusters for different workloads, because the
Is it this one, the Lift Presto gateway?
Yeah, I think so. Yeah, then you have to build up the gateway to route the traffic to the right Presto cluster.
Perfect. Okay, great. So it is the Lift Presto gateway. Yeah. Our next question here is, to overcome fragmented address space issues with multiple HDFS clusters, have you tried AWS Outposts?
Actually, we haven't. So I think like many other companies, our philosophy is to use open source and free software as far as we can. Sometimes it's not just because of cost, but also we need to maintain sort of spirit in the engineering team, so that people are excited by exploring new technologies and learn things by doing things, not just using existing software or services. Sometimes it's too easy.
Great. Our next question here is Presto related. Are you using the Hive connector to have the metastore? And if not, which mechanisms are you using for mapping Alluxio directories to catalog schemas tables/partitions?
So yes, we are using a Hive connector, but it's I think it's a version already adapted by Alluxio. It's called Alluxio connector, Alluxio Presto connector. Because the Presto architecture allows for external connectors to be loaded into the system and taught to have metastore. So this is quite feasible and works pretty well.
Perfect. Here's another follow-up question related to the Presto gateway. So do you deal with auth-n and auth-z in gateway level or in Presto level using Ranger or IDAP?
We use auth-z in Presto gateway level. And actually, because we are a big company, we are using SSO. So the user, we have many customers to the system. So when they log in, they are authorized, and their login profiles are directly used here.
Great. And have you considered using multiple metastores to restrict who can query what data?
That's a good question, but I think we will start from using just one Hive metastore, because you can use you can authorize, you can grant different privileges to different users in one Hive metastore. But certainly we have to solve the scalability and that kind of issues in one Hive metastore. And I think having multiple Hive metastores, you will increase the operational cost, right? So better not to do that. I think one Hive metastore should be able to handle it.
Great. And is Alluxio deployed in Kubernetes or EMR?
Which one?
In your didn't specify.
Presto?
Alluxio.
Alluxio. So actually, we are building that by ourselves. We have already built the Presto cluster co-located with Alluxio. And I think EKS and EKS definitely is one possibility, but I think that probably requires a little more human resources to handle that. And EMR, as I just said a moment ago, we are trying to use open source technologies directly.
Great. Are you using one big Alluxio cluster or multiple?
Multiple. So I think Presto will achieve the best performance by co-locating with the computer engines like a Presto or Yarn. So I think it's better to take some extra hassle to configure Alluxio together with other computer engines so that they are co-located. But I think in some architectures, it may also be good to have one specialized caching cluster to run Alluxio.
Excellent. How does the system behave differently under streaming versus batch-like workloads? Does data on demand cause halts in streaming flows?
Just streaming. Let's see that.
Question here goes, how does the system behave differently under streaming versus batch-like workloads? Does data on demand cause halts in streaming flows?
Yeah, I think it's a very good question. I hope we can answer that question in 6 months.
Perfect. This is future work.
Right. So because this project is huge, I have to bring all the teams to the same page, and we're making very good progress in terms of that. So we have been moving faster in the Presto use case, but a little bit slow in the Yarn use case because we have the engineering resources have been pretty tight. You can only focus on one thing at a time. And we do have in the picture the streaming workload. Pretty much we have decided to use Flink. I think in 6 months, probably in the summer, we should be able to answer that question.
Excellent. Our next question here is: do you use Alluxio catalog?
Yes. So we are testing, and that catalog service was only recently released, right? So we need to spend some time test it in production. We have already started on that, and so I think we are using that in the Presto use case, as you know. Currently, it's only for reads, and the writes will be released in a few months, I believe. So we are currently testing the reads workload on Presto, and should be in production in a couple of months.
Great. So our next question here is a bit of a controversial one, perhaps. Question is, or perhaps is a statement, many people are saying Hadoop is dead. What are your thoughts around this?
That is a tricky question. Hadoop is dead. I think people, when saying that, people probably mean some new trends are going very strong, like EMR and Kubernetes, right? So you can manage your computer resources, use EMR on demand, or use Kubernetes after spending a lot of effort yourself. But I think in bigger organizations in general, you have tons of legacy workloads running on the legacy clusters like Yarn, Hadoop, or even HDFS. You cannot just say, oh, those are dead. We have to move everything to the new stacks like Presto or EMR. That takes tremendous amount of compute resources and also a lot of engineering resources. I think probably that's not worth doing. I think in the case of Facebook, although they are the birthplace for Presto, they only choose to implement a new ETL jobs on Presto. They're not even considered to migrate all the legacy systems to Presto. That said, the dying Hadoop technology still has its place in organizations and serve very good purposes.
Great. I think there's a clarifying question here. Are you running Alluxio on top of Kubernetes?
No, we are not doing that yet. As I just said, to do that, it's probably doable, but Kubernetes is a relatively new technology. Moving everything to Kubernetes may not be practical. It takes a lot of time. You have to figure out things by yourself. Sometimes it's a luxury in organization.
Mm-hmm. Great. Our next question here is, could you quantify what are the major sources of tickets? What are the distribution of faults now that you are down to roughly around 10 to 20 alerts a day?
Oh, yeah, it's good. Good question. So I think the types of alerts we receive. So if you look at the Hadoop cluster, right, you have all kinds of components. Like some nodes are down, some services are not responding, and I think in our case, because we have the ETL cluster is very big, as more than 500 nodes, right? And for some reason, for cost reasons, we are using H1 nodes for to run Hadoop. Those nodes have they're using hard disks, which is very old technology. You very easily can see a few nodes dead or several disks there in your cluster every day. So I think most part of the alerts are one-sided alerts. Most of those are false alerts because we were not able to keep the monitoring configurations in sync quickly. The cluster, you often have to replace data nodes, and you often need to add new nodes or terminate some bad nodes. So if you don't update, if you're not able to update your monitoring configuration, for example, in a week, then you have a lot of data nodes that are already being monitored, but they no longer exist. And so things like those, they generate a lot of false nodes, and then the operation team have to dig into all the alerts to figure out which one are false, which one are true. That's a tremendous amount of cost.
Great. Our next question here is, now that you're moving on to the next phase or next stage of the second project, the re-architecting project, what are you focused on for the next phase?
So we roughly divided this into 3 phases. The first phase, we are focusing on Presto, make data scale and work and have the performance we need. And second phase, which we are planning to start in the next quarter, we are going to rebuild the young cluster so that we can quickly migrate all the legacy jobs into the new cluster with the benefit of having Alluxio. That's the second phase. The third phase after this is we can retire the legacy clusters.
I had a chuckle there when you said the third phase is to retire. Great. So thank you, Du, for an excellent session right now. We're coming close to the end of our time here. I see there are a couple of folks still typing. We may have time for one more question. Okay, here we go. So the last question is, for EA's Black Friday scenarios, what is the typical point of failure or hotspot besides ramping up and down? The typical point of failure or hotspots in these sort of Black Friday scenarios.
Yeah. Failure hotspots. Yeah, I think that is probably related to the SLA.
The SLA.
Yeah, SLA has been a huge problem. You can see the SLA curve goes up and down quite a bit because in the peak hours, the Black Fridays, I think the Hadoop cluster definitely have a lot of problems. One problem is related to the scheduling of jobs. It's very weird. Like when you have a daily job, right? we can have hundreds of daily jobs. All the daily jobs will start at the same time, 0 UTC, something like that. They all computing for the same pool of resources. Then the jobs don't get the resource they miss SLA.
So inconsistent and sort of unpredictable SLA.
Yeah.
And scheduling issues.
Yeah, that's a huge issue in the Hadoop cluster. That's why it's going dead, right?
And we have 2 minutes for a follow-up to this, which is, do you use some low latency stores and different databases apart from Alluxio and Presto to support some of the use cases for Black Friday scenarios?
Yeah, we do. We definitely do. So on the ad hoc query side, when the team started, we used the Hive, and then last year we are moving to Presto. At the same time, we are also using Redshift and more recently we are introducing Snowflake. Yeah, and across all our clusters, we have some other technologies like Cassandra.
Excellent. Well, that's it for us today. Thank you again, Du, for sharing your experiences and lessons with us.
A pleasure. Thank you very much.
And thank you, everybody, for attending. I know there are a couple of folks with more questions, and you can feel free to join the Slack channel. Du is also on the Slack channel if you have any follow-up questions. And then we look forward to seeing you at our next online event. Thank you, everybody. Have a great week. Bye.